Hey, hi everyone. Good morning. Let's start. My name is Andreev, and I'm an assistant professor here at CU Boulder, working on superconducting qubits. And it's my honor to introduce Angela Ko from the University of Illinois at Urbana-Champaign, and she's going to talk about coupling an Andreev spin qubit to the Transmon.
Okay. Can everyone hear me okay? I think it's working great. Okay, so thank you for the organizers for putting together this workshop. It was really interesting yesterday to hear about all the quantum error correcting code. I'm going to talk about something completely different. So now for something completely different, today I'm going to share with you our work coupling an Andreev spin qubit to a transmon. So I think most of you are familiar with what a transmon is. We'll still go over it, and I'll go over what an Andreev spin qubit is and how we've implemented it in our group. So I've also gotten permission from the session chair. So if you want to ask any questions to me during the talk, that's totally fine for clarification, for any clarification or anything like that. Okay, so first I'm going to ask a question. Yes. Okay, how should we build a quantum computer? So I for sure do not know the answer to this question, but I hope by the end of this workshop, no pressure, we'll all figure out the answer together. But in the meantime, we can think of two possible approaches to building a quantum computer. So the first approach is imagining that we have this one amazing qubit that is just a single physical platform that we're going to use for both memory and processing. And this may happen. We can maybe able to build this amazing platform, but it is kind of a difficult ask, right? So we're looking for something that can satisfy the requirements of doing all possible tasks. And some of these tasks might have conflicting requirements. So if you want to build a memory, you might want it to be well isolated from the environment. But if you want to do processing, you actually want it well isolated from the environment. But if you want to do processing, you want it to be both well isolated from the environment, but you should still be able to access it fairly quickly so you can do fast processing or fast readout. So it might be difficult to satisfy all these requirements for a single platform. The other approach we can think about is trying out different platforms specialized for each purpose. So we can take a page out of our computers now and think about trying different platforms for memory, for maybe a fast memory, for fast processing. And there we can kind of relax having to satisfy possibly conflicting requirements for each specific physical platform. So you can imagine maybe you want to use trapped ions for a memory, maybe you want to use spins for a fast memory. Maybe you want to use superconducting qubits for fast processing. Maybe you want to use Rydberg atoms for slow processing. There is also still a difficulty with this. So we relax some of the requirements within each platform, but then we need to think about how to make interconnects between all the different physical platforms. So we need to convert between platforms that might have different underlying physics between them, and you might need to convert from something that stores its information in the magnetic field into something that stores its information into the electric field. So these can also be challenging. I'm going to focus on the second approach. Doesn't mean that it's better, but I'm going to focus on it for today and discuss using coupling between spin qubits and superconducting qubits. So you might imagine that for a spin qubit, we would like to use that as a memory because it's fairly compact. So you can have a lot on a single chip, and it typically has pretty long lifetimes. And then so it's well isolated from the environment. And so you store your information and it stays there. And then you only need to access it when you want to pull that information out. For superconducting qubits, you might imagine that it's good as a manipulation qubit. We can make really high fidelity operations in a really fast time. And it's also fairly easy to remotely couple different superconducting qubits to each other because they have a pretty big footprint. But it can be difficult to couple spin qubits to superconducting qubits, right? Because spin qubits can be very compact. They have a very small footprint. Superconducting qubits are fairly large. They can be on the order of many microns or millimeter size. And then so this difference in spatial footprint and also possible difference in the way that we store the information in the spin qubit versus in a superconducting qubit can make it difficult to couple them to each other. However, there is one type of spin qubit that is fairly easy to couple to a superconducting platform, and that is the Andreev spin qubit. And this was realized in an amazing experiment by the Devray group, and you can ask Max or Kyle about the details of this experiment. So with an Andreev spin qubit, what you're doing is you're storing your spin qubit in the junction, in a superconducting junction. And then that superconducting junction is going to affect the current through your superconductor, and that current can easily be coupled to a superconducting resonator or to a superconducting transmon. So I'm going to focus today on talking about Andreev spin qubits and how we implement them and how we couple them to superconducting transmons. Okay, so this is the outline of my talk. I'm going to discuss building an Andreev spin qubit using a superconducting quantum dot junction. And then we're going to use a transmon to actually read out our superconducting quantum dot junction. And then I'll show our results building this, operating this Andreev spin qubit as a qubit, and then also coupling it to the transmon. So we'll start first by going over what an Andreev spin qubit is. I think we're not all so familiar with what a spin qubit is, so we can start by thinking about potential in a well. So if I have a particle bouncing back and forth in a potential well, then this particle bouncing back and forth creates some standing waves, and these standing waves will give you some energy levels. And then so for a Andreev spin qubit, we can now replace the barriers of our potential well with superconductors. And then what that does is it changes the boundary conditions of our potential well. And then so if my particle is bouncing back and forth, actually when it bounces and hits the superconductor, it's going to, if I have an electron, it's going to reflect as a whole. And then these are going to determine the energy levels of our potential well. And so if you want an optics analogy, this is like the superconductor is acting as a phase conjugating mirror. Okay, so for these, for a superconducting potential well, the energy levels look like what's shown here on the right. And then so we have the ground state being our energy level being unoccupied. And then the particles that we're going to use in the system are actually superpositions of holes and electrons. And then so our first excited state is going to be a single quasi-particle. It has some well-defined spin. And then I get two energy levels that have different spins. And then my next excited state are two quasi-particles occupying my energy level. And these two states, so the zero and the two quasi-particle state have even parity, and the single quasi-particle states have odd parity. So it's difficult to transition between the even parity and the odd parity. And then so what we're going to use as our spin qubit is these single quasi-particle states of spin down and spin up. And then so the astute among you might see that these two are actually degenerate at zero magnetic field. And then so they can be very difficult to operate as a qubit. But if you add, you do a materials trick and you have some spin orbit coupling in your potential well, what you end up with is that the spin is actually coupled with the current. And that coupling will actually open up a small gap, allowing you to use your quasi-particle spin as a qubit. And so that's nicely illustrated in the figure paper of the spin actually coupling to the direction of the current. And if you have a different spin, it'll change the direction of the current. So if we have that, then it's fairly easy to couple it to a superconducting resonator. So if you incorporate your junction, which is shown here, into a superconducting loop, if you apply some flux, you'll get a persistent current that will flow in different directions depending on the spin state of your junction. That could be coupled to a resonator. If you measure the response of your resonator, and you look at the in-phase and out-of-phase quadratures, what you'll see is that if we're in this ground state, you have some resonator response. If you're in the spin state, you'll have different responses for being in different spin states. So this is the first implementation of an Andreev spin qubit. It was amazing. There's also some work done at Saclay on these type of junctions, but there are some non-idealities associated with these Andreev spin qubits. So if you look at the resonator response, the darkness of the response will tell you, or the intensity of the response is telling you kind of how much each state is occupied. So it looks like the states that we want to work with are not occupied very much, and it's mostly just in this ground state that we're not going to use as our qubit. So we want to use these different spin states as our qubit, but the device mostly moves outside of our qubit subspace. So we get this problem where the qubit states are excited states. We typically get some leakage out of the qubit subspace, and it's difficult to initialize the qubit into your Andreev spin state. And the operations were done via Raman processes, and those can be fairly slow. So we can try to see if there's a way for us to solve these non-idealities by changing the system a little bit. And what we're going to do is, instead of having this junction, we can add in a quantum dot into our superconductor. And what this quantum dot will do is it's going to prefer to have our energy states be single quasi-particle states. So if we're in the regime where the superconductor dominates, it's going to prefer having even parity, so having 0 or 2 quasi-particles be our ground state, so very similar to our superconducting junction that we had previously. And then our energy diagram is going to look very similar to what it was before. So we have unoccupied states. This first occupied state is now separated by some single particle energy that's determined by your dot. And then you get quasi-particle states, spin states down and up. And if I need to add an additional quasi-particle, there's that additional single particle energy plus some charging energy, because you now have this isolated electronic system. So there's some interaction cost for having multiple quasi-particles on your dot. What we can do, though, with our superconductor quantum dot superconductor system is we can adjust the energies and the coupling between the dot and the superconductor. So instead of having strong coupling to the superconductor where it dominates the dynamics of the system, we can have the quantum dot dominate the dynamics. And in that case, it prefers to have single quasi-particles jumping back and forth. And so our ground state now, instead of being the unoccupied state, becomes one of our spin states. So we can tune ourselves from, let's say, the left regime to the right regime, so we can eliminate this problem of our qubit states being the excited states of the system. And then so typically on the left side, this is known as a singlet. And then on the right side, this is known as a doublet. And we want to tune into this doublet regime so that our spin states now become the ground states of our qubit. Yeah.
Are the excited states still like metastable, or is there like a decay process?
Yeah, they're still, the idea is that you can go between kind of these two states typically, because those maintain parity. But in this case now, it's very difficult to transition from here to here. So it's useful as a qubit because I can only really transition between. Does that answer the question?
Well, I'm also kind of wondering whether there's a decay process that you have to combat from the excited state to ground state, coming from an atomic physics background.
From the
Yeah.
from this state to here?
Or to
here.
from that state to anywhere, since it's an excited
So
state.
from this state to go here, it's similar to how a typical qubit operates. So if you have like some relaxation that couples like magnetically, let's say, between these two, then you would get transition from the upspin state to the downspin state. From here, it's a little bit more difficult because this requires that you get an extra quasi-particle from the world to get yourself from here to here. It does happen. That's our secret in superconducting qubits, but in our device, it happens about once every few milliseconds. Okay. So we're going to try to now build this system, our superconductor quantum dot system, to try to eliminate these qubit states being our excited states. Okay, so now I'm going to discuss how we actually built this spin qubit. So I'm going to quickly go over a transmon. I think we're all familiar with it. So a transmon is a Josephson junction in parallel with a capacitor. So this is the Hamiltonian for our transmon. Our N is our EC is given by the charging energy. We can determine this by a capacitor, and our N is the charge on this island here. And then we have some Josephson energy given by our junction, and then the Josephson energy depends on that phase difference across our superconducting junction. So our transmon is operated in an EJ much greater than EC regime. So we get a potential that looks like an anharmonic oscillator, and this is the most widely used superconducting qubit. I think these coherence times may actually be much higher than 400 microseconds now, with operations on the order of tens of nanoseconds. Okay, so but for most of this talk, what we're going to use the transmon is actually for readout. And what we're going to do is incorporate our superconductor quantum dot superconductor junction in a squid geometry. with our transmon. And then so now we add to our transmon Hamiltonian this extra term due to the superconductor quantum dot superconductor junction. And depending on what the ground state of the system is in, the extra term is either going to have a cosine phi dependence or a cosine phi minus pi dependence if we're in this doublet state. And this pi comes from the fact that the Andreev process actually talks about tunneling current from one superconducting lead to the other. And if you have a single quasi-particle as your ground state, you're actually exchanging quasi-particles, so you get a pi phase. So that's where this cosine phi minus pi comes from. And if we think about what our transmon response should be in this case, so if our quantum dot potential has this is in the singlet state, then we have this familiar cosine where the minima is at 0 phase difference. But if we have our doublet state, we have this pi phase shift, so our maxima is actually at 0 phase difference. We add that to our reference junction, which just has this familiar cosine phi behavior. Then if we sum that up, what we end up with is if you're in the singlet state, you get a deeper potential well, so the transmon frequency is going to be larger. And if we're in the doublet state, we get a shallower potential well, so our transmon frequency is going to be smaller. And then so this is how we're going to be able to distinguish between our singlet and our doublet states. The transmon frequency itself is going to be larger in the singlet state and smaller in the doublet state. Okay, so the device actually looks like this. It's a planar 2D device. We have an asymmetric feed line with four devices hanging onto it. And then so we are going to perform standard spectroscopy using our resonator and transmon. And then so our resonator is formed from this capacitor shown in yellow and this large inductor here. And then we have a transmon that's made using this, the capacitor transmon is made with this large pad. And then our squid loop is shown here in the center. And our junction is actually not the typical aluminum and oxide junction. We have a aluminum deposited on indium arsenide, and our junction is just going to be etched, a small region that's etched away of this aluminum. And our quantum dot is going to be a larger region that's etched away, but we have 3 gates under it that can control the potential in our quantum dot. The way that we do our experiments is we can send in a response and look at the transmission through our feed line. And for when we're at the resonant frequency, the magnitude of the transmission is going to decrease at the resonant frequency of the resonator. If we now want to do two-tone spectroscopy, so we want to look what the frequency of our transmon is actually going to be. That's what we're going to use to see what the ground state of our system is. What we'll do is if we send in a tone, if we excite our transmon, the frequency of the resonator will change. If the transmon is excited compared with the frequency of the transmon, if frequency of the resonator, if the transmon is in the ground state. So this is, it's in the dispersive regime. So the frequency of the resonator changes depending on the state of the transmon. And so if we look at fixed resonator frequency, we can figure out what the frequency of our transmon is going to be. Okay, so what we can do now is try to tune ourselves from the singlet state to the doublet state. So if we have our quantum dot, we are going to we're going to change what we call the plunger gate. That's a linear combination. That's mostly the center gate with a little bit of contribution due to cross capacitance from these side gates. And we can start in the singlet regime where the ground state is still this unoccupied level. And what we can do is by changing our plunger gate voltage, we move that single particle energy downward. And then as we keep changing that plunger gate voltage, we can actually make the single particle energy negative. And then we end up in the doublet state. And then so that's the experiment we want to do. And again, we're going to look at the transmon frequency. If we're in the singlet state, we have a larger frequency. If we're in the doublet state, we have a lower frequency. And so if we perform this experiment as a function of our plunger gate voltage, what we see is that our transmon frequency changes, but there's these quick jumps that occur, and the frequency quickly jumps from being larger to smaller, and then back. And then so we think that what I'm showing above is what's actually happening in this experiment. And then if we change the flux now to half flux, we expect the reverse behavior. And then so we end up with over the same gate voltage range, we have a lower frequency at external flux equals pi, and And then we have this jump to being in the higher frequency as we move our plunger gate voltage. So we think that if we're in this regime, we're in the singlet state because it has larger transmon frequency, and if we're in this regime, we're in the doublet state because it has lower transmon frequency. And we can also calculate what we expect the transmon frequency to be a little bit more quantitative than the cartoon I showed. So what we're doing in the x-axis for the series plot is changing that single particle energy using our plunger, and then we see that we expect that if we're in the singlet state, we expect these jumps in the transmon frequency and the reversal happening at the external flux equals pi. Okay, so we can further confirm this, that we're actually changing the ground state of our system by looking at the phase dependence. So for our singlet, we have this cosine phi. For our doublet, we expect a cosine phi minus pi. So if we start in the singlet state, our maxima in frequency should occur at 0 or 2 pi. And we indeed see that. And then as we change our plunger gate voltage, we see that our minima is now at 0 and our maxima is now at pi. So we see that we're reversing our phase dependence here. And then so if we take cuts, then we end up with, we're in the singlet state, we have this familiar cosine phi where maximum frequency occurs at 0, minimum frequency occurs at half flux at pi. And if we tune into the doublet state, we have a pi phase shift. So we end up with minimum frequency at 0 and maxima at pi. And if you're in the regime where the energies are close to each other, we actually see both curves. So we can now tune between the singlet and the doublet state. We have this gate voltage that we could use to push us into the doublet state so that we can operate our spin qubit such that the spin state, one spin state is the ground state of the system. We can also apply a magnetic field. So if our energy levels look like this, if we apply a magnetic field that gives some Zeeman energy splitting between the two spin states, so we can push that down. And then so if we're at low magnetic fields, we can start in the singlet state. So maxima is again at 0 or 2 pi. And then if we increase the magnetic fields, we end up in the doublet state where the maxima now occurs at pi or minus pi. So we also have magnetic field driven parity transition. Okay, so we can tune between the singlet and the doublet state. So if we're safely in the doublet state, then we get rid of this problem of our qubit states being excited states. But now let's see if we can try to also help a bit with performing gates a little bit faster in this Andreev spin qubit. Okay, so I'm gonna discuss that now. So I mentioned that we can tune between the singlet and the doublet state. We actually want to be able to distinguish between being in the different spin states. So we're going to add this spin orbit coupling that I mentioned a little bit earlier. And if we have this spin orbit coupling, our potential now changes again. It adds a little bit of it. What it does is it shifts the spin states relative to each other for these potentials. So if I'm in the doublet state, I have two possible spin ground states, and their curves are going to be shifted. The potentials that they create for the transmon are going to be shifted relative to each other. And then so if I sit here, for example, then I will be able to distinguish which spin state I'm actually in. And then so the form for the potential now has this additional either plus or minus sine phi term that we add to this potential. And then so I end up with kind of two manifolds for my S quantum dot S system. And I want to operate in the S equals 1/2. This is what we called our doublet manifolds, where I have a transmon that transitions, that has a specific frequency for being in the down state, and then for my spin state being in the down state, and then a specific frequency for my spin state being in the up state. And there's nothing forbidding transitions from the down to direct transition from the down part of my spin to the up part of my spin. So maybe you can also enable this kind of transition and do some fast operations. Okay. Our singlet state has even parity, so it's very difficult to transition between these two different regimes. So we'll have transitions for the transmon if we're in the singlet state, but we won't be able to couple between the singlet and the doublet. Okay. So we can again look at our transmon frequency and actually see that we're able to distinguish between the two different spin states. So if I'm in the singlet regime, I have a single curve that corresponds to my transmon state that corresponds to my transmon frequency when I'm in the singlet state for my spin qubit. So there's two manifolds now, one corresponding to the spin qubit. And for that specific spin qubit state, the transmon frequency is going to be different. And then so if I'm in the spin 1/2, that being the ground state of my system, so if my spin states now become the ground states, then I end up with these frequencies for my transmon. So this frequency corresponds to the spin state of the Andreev spin qubit being in the up state. And this frequency corresponds to the Andreev of the transmon corresponds to the Andreev spin qubit being in the down state. So if I look at what frequency is what the transmon frequency is, I will always be able to distinguish which of my spin states I'm in. So my transmon is acting as my readout mechanism in this case. Okay. So we also want to be able to tune the spin frequency. So maybe you want to tune into a place that's more convenient for operation and more convenient for processing. So what you can do is that you can apply a magnetic field, which will split. So it will make this splitting but larger or smaller. And what that does is it changes the potential that's felt by the transmon. So if I apply a small magnetic field, I'm going to make the spin down state. So this is the potential felt by the transmon. More is going to be lower in energy than the spin up state, which is shown here in red. And then so you can see that if I now do my transmon spectroscopy experiment where I'm doing readout, the lower energy state, which corresponds to this one, has higher visibility because it has a larger thermal occupation compared with the higher energy state, which has a lower visibility. And now if I separate these two spin states even more, then I change the visibility stronger so that I only basically see that my transmon frequency corresponding to being in the spin down state compared with being in the spin up state where there's very small visibility. So I can truly tune my spin down state to be the ground state. Okay. So now we can try to perform transitions between the spin down and the spin up state. And so now we're just going to directly drive the spin transition. And we can indeed directly drive that. Its dependence as a function of external flux is shown here. And perhaps more useful is looking at its dependence as a function of the magnetic field that we apply. So if I apply a magnetic field to spin states, what it's going to do is going to open Zeeman energy splitting between the spin down and the spin up, and that should have a linear dependence, just G mu B. And we indeed see that it has a linear dependence, and we can tune the frequency of our spin transition and also drive it. And then if we can drive this transition, then we can also do Rabi oscillation. We can do Rabi driving here. So that experiment is shown here. We apply a Gaussian pulse with some amplitude and some width, and then we read out our spectrum. And then what we can do is take a cut as a function of the pulse width, and then also look at the Rabi rate as a function of amplitude. And then so the Rabi rate, as one expects from the Rabi equation, will increase linearly for a two-level system as a function of amplitude. And then so we see that we can drive transitions with Rabi rates up to say around 200 or say almost 300 megahertz. And we get a slight non-ideality that is actually coming from our electronics and temperature. So we can drive these very fast transitions now for our Andreev spin qubit. We can also look at its lifetimes and coherence times. And spoiler, it's not yet ready to be incorporated it's not yet at the level that we would like for the lifetimes and the coherence times. So if we look at the energy relaxation, the T1 is on the order of 24 microseconds, and the T2 Ramsey is on the order of 11 nanoseconds, and echoes 37 nanoseconds. If we do a few more echoes, it improves, but not by that much. So I do want to emphasize that we've kind of fixed some of the non-idealities, right? We've made our qubit states we've gotten rid of this leakage issue. So our spin states are now the ground states of our system. And we've also made driving much faster, but it hasn't actually made the T1s or the T2s worse in the Andreev spin qubit. So if we compare it to previous implementations, the spin qubit lifetimes are very similar. The Andreev spin qubit lifetimes are very similar, and the coherence times are also very similar. And we do think that there's a path forward for this. So we think that the coherence times are limited by having a nuclear spin math. This is the age-old problem in semiconductor spin qubits, which is that the nuclear spin in indium arsenide is really high. So we can look at a material that has lower nuclear spin. We expect these coherence times to get longer. And then there's also, we think that there's some dielectric loss associated with our dielectric that we're using for building these spin qubits. So something that we're currently working on in our lab is actually to build superconducting circuits in germanium. So germanium can be nuclear spin free, so we expect the coherence times would be much longer. There's also been experiments demonstrating that you can have induced superconductivity, so we can build these Andreev spin qubits, and they also have very stable electrostatic control over their quantum dots, indicating that their dielectrics are really quite good. And we started to pattern some resonators on germanium, and my lab is currently working on building superconducting circuits in germanium. So as a last thing, we have this transmon that we've been mostly using for readout, but it is also a qubit, right? So we can also quantify how well we're coupling the Andreev spin qubit to the transmon. And then so we had these transitions before, so we have transmon transitions, and we also enabled our spin transitions, but we can also look at swap transitions between the transmon and the spin qubit, and those are shown here in dotted and dashed. And we can drive those transitions as well as a function of flux. And then so these can be used to, if you wanted to create 2 qubit gates between the Andreev spin qubit and the transmon, one could do that. We can also tune our spin transition frequency in resonance to the transmon transition frequency to get a sense of how strong the coupling actually is between our spin qubit and our transmon. The splitting puts us well within the strong coupling regime, which is our coupling between the transmon and the Andreev spin qubit is larger than either the lifetimes or coherence times of the spin qubit and the transmon. So you can perform gates between the transmon and the spin qubit. So in conclusion, we've mapped out this full phase diagram for the superconductor quantum dot superconductor junction. We built an Andreev spin qubit using the superconductor quantum dot superconductor, and we have observed strong coupling between a transmon and an Andreev spin qubit. If you want more details, you can look at these 3 papers on this work, or ask me. That's also good. And so a lot of people worked on this experiment. The main grad students on it are Arno and Marta, that is possibly going to be a postdoc. So if you're interested, please talk to me about that. And then Randy is working on building the superconducting circuits on germanium, and that work is funded by our NSF Center on hybrid quantum architectures and networks. And if you want to learn more about what we do in my group, so you can visit our website at qubitlab@qubits.physics.illinois.edu. You never know what you're going to find in Illinois. So thank you for your attention, and I'm happy to answer any questions. Okay.
We have about 10 minutes for questions.
Hey, thanks. That's a beautiful results, actually. This T1, T2 of the spin transition, it was under magnetic field, right? Did you try to measure at 0 field?
The problem is that the transition frequency gets really low at 0 magnetic field, and then so it's difficult to drive the transition.
But can you pass flux to like
so we haven't done that
come back?
Yeah, so that's a good suggestion. We haven't done that experiment, but we can try it and see if our T1 gets longer.
You expect T1 to get much longer, right?
Yeah, maybe. We'll see.
Hey, Angela.
Hey.
Thank you for the talk. So for your initialization, your like loading of the Andreev spin qubit.
Yeah.
Maybe I missed it. Did you quantify exactly how, like, what population you are in the doublet versus the singlet?
Yeah. So I didn't actually put that in the presentation. So depending on how we tuned such that we're deep in the doublet state, basically is 100% in the doublet state, but there is some quasi-particle poisoning that sometimes happens. But because we have this charging energy, it makes it a little bit slower than typical superconducting qubits.
Yeah.
So we can stay in the doublet state for a few milliseconds before it actually goes
Okay.
into the singlet state.
So it's milliseconds of stability in that manner. Okay.
Yeah.
And then as a follow-up, can you comment on sort of like where that level, where your dot level sits relative to the superconducting gap? In that situation?
It is much smaller than the superconducting gap, but I don't remember off the top of my head exactly where it is relative to the gap. The charging energy is much larger, but
Yeah.
the single particle energy is significantly smaller.
Yeah.
So if the decoherence comes from nuclear spins, I would have expected that dynamical decoupling would have helped much more.
Yeah,
Yeah,
but I think the problem is that the coherence time is so short to start that our high pulse is not good enough, right, to perform really good dynamical decoupling.
I have a question. So besides the quasi-particle poisoning stuff, which is kind of millisecond scale, do you have to worry about like long-term offset charge noise stability? Does that affect the effective gate polarization charge?
I think that it does. I think our dielectric is not state of the art. So so one thing that we're doing is working with the spin qubit who work really hard on making sure their charge noise is pretty stable so that they can get these high fidelities. And then so that's something that we can improve.
But do you see it? I mean, do you just measure a charge offset that's drifting in time or jumping? In time?
We don't actually, so on like the day scale, we don't see jumps.
Hi, thanks for the really nice talk. You mentioned that you thought the T1 might be limited by dielectric loss.
Yeah.
That means you think it's coupled to the charge operator of the qubit, or did you mean something else?
I actually mean that the transmon here was not super good. And then so the dielectric loss of the
You mean it's like
transmon,
Purcell limited through
yes,
the
it actually was Purcell limited.
transmon? Shouldn't it scale with like the detuning from the transmon? Does it follow that behavior?
That I'm not sure about. I think that so I can show you you have gamma for the transmon. The transmon gamma is only about 1 megahertz. And then we operated it at like the spin qubit at around like 11 gigahertz. So it should be pretty far detuned, but I still think there's some limitation of the transmon due to the.
Okay, cool. Yeah, that makes sense. Thanks.
If it's coupled to charge, anyway, you can use this to turn the transition into a clock transition to get insensitive to magnetic fluctuations.
This is like a very layered question. It's possible. I think that we have to make the transition significantly better to actually look at to actually make it into a usable clock transition, right? If we're trying to go to do the spin charge first.
Yes, taking like T2 as a function of magnetic flux, like tune in and out of this regime where you get like more sensitive to charge versus magnetic field.
So we haven't done that experiment, but I think I think it's possible, but we haven't done the experiment yet. Oh.
In your plot of the spin qubit frequency versus field, does it sort of match sort of an expected G factor for indium arsenide, or
Yes.
is it very different?
Yeah, it's actually quite similar to the expected G factor. So in these experiments, we can actually both measure the G factor and also the spin orbit coupling energy. So you can also learn some interesting things about the materials that we're using.
Hi, thanks for the talk. Can I fabricate multiple quantum dots in the middle of this junction and get it to couple to the transmon? I guess like I'm thinking about like, can I make a singlet qubit to get me
Yeah, I think you could.
like magnetic insensitivity?
Yes, but then you'd get like, you'd have, yes, you could do that.
But like that regime might have like a S equals 0 subspace, right? Will the singlet triplet states pull on the transmon in the same way?
They will pull on the transmon, but what do you mean in the same way?
Like, will you get a frequency shift as a result of being in the singlet versus the triplet?
Oh, yeah, we do that. So even if you just look at like a junction without a quantum dot in it, the S equals 0, you'll get some resonator response, and then the different spin states also have.
Oh, cool. Nice.
Any last question? Time?
Okay.
Thank you, Angela. If I understood your readout scheme, it was usually to look at the frequency of the transmon,
Yes.
but that's rather slow, question mark. And can you think about doing it faster or?
Yeah, that's right. So it's slower than the resonate. So we can try to think of ways in which we actually couple, because it's going to be like kind of spin qubit through transmon to resonator. It's difficult to make that interaction really strong, right? If we just want to do basically directly resonator readout of the spin device, and then so sort of slow, but doesn't have to be that. So still on the order of like microseconds for the speed. So still slow, but not insanely so, I would say.
Okay, understanding. Don't you have to sweep a spectroscopy tone in order to see the frequency of the transmon, or how are you seeing the frequency?
We have some idea of the, so we do have to sweep, but it's over a very small range in frequency. So we have some idea of that. And then once we know that frequency, then we can perform readout. Like we can do the same thing we do with the resonator, where you just sit at the transmon frequency and then see that it's not that transmon.